So what is early verification and how can it help you improve your control system performance? Well, to answer this, let's step back and first talk about the problems you are facing in developing control systems. Machinery and devices across many different industries continue to become more complex with the need to differentiate themselves from their competitors. This differentiation often comes from the use of embedded control systems. Here is some data taken from a study of companies developing electromechanical equipment performed by the Aberdeen Group. Table 1 here provides data supporting what I just mentioned. You live in a very competitive marketplace where your customers want better products while your management wants you to develop them faster and cheaper, and the differentiation is often accomplished by putting more software and electronics into the product. Table 2 here is interesting because it illustrates the challenges you have in designing your electromechanical systems. These challenges can be reduced to two main points. Finding mistakes early in the development process is no easy task, and designing a multi-domain system is hard to do. So why do we need to find errors early, and why did people list it as an important challenge? Here is a study by NASA that answers these questions. The x-axis shows the phase where the error is found and fixed, and the y-axis shows the relative cost to fix the error. The bar color corresponds to the project phase where the error was introduced. For example, the most expensive type of error to fix is an error that is in the requirements that is only found during testing. It is very expensive because you will need to go through the whole development process to fix it. Not only expensive, but also time-consuming. So finding errors early means that we can develop our products cheaper and quicker, and that is why it's so important. So let's look at a simplified representation of a traditional development process to understand why it is difficult to find errors early in designing multi-domain systems. The complexity in systems is dictating more complex specifications, and since teams rely heavily on document-based specifications, it gets harder and harder to interpret them correctly. The microcontrollers or PLCs are programmed directly from the specification, but this is done separately from the development of the control algorithms. These separate workflows can result in problems if the tools used don't connect to each other. The controller algorithms are mainly tuned on a prototype or on the actual system, and the integration and test phase is where the problems show up, since this is the first time the system is integrated. The result is the errors are found late and they are expensive to fix. So let me introduce model-based design and explain how it will help you detect errors early and therefore allow you to design innovative products with higher performance, faster and cheaper. Model-based design is a computer-aided engineering solution for mathematically describing how the equipment will work. The key to model-based design is that you start with a block diagram that mathematically models the system behavior. By being able to model the system behavior, you can then use dynamic system simulation to try out your ideas. First, you get an understanding of the overall system that you are building early in the design, and with this, you can try out different design alternatives and do initial what-if studies that would be too risky to test directly on the system. For engineers, block diagrams are easier to understand than text because they are visual. In essence, a block diagram complements the text requirements to communicate design intent. Actually, you can take the text requirements that you have and electronically connect them to your model to show which part of the model implements which requirement. The model is elaborated to include all the different elements of the design and operating conditions. You can reuse existing intellectual property and engineering data from existing designs and tools that you use, such as CAD, FEA, and SPICE. The model is not only a graphical representation of your design, but it can also simulate. Therefore, we say the model serves as an executable specification. So the fact that the model is visual, easy to understand, and executable removes the ambiguity from interpreting these text requirements. We can start testing the design and requirements through simulation of the system model very early in the process. And we can then rapidly iterate on the design, continuously testing and ensuring that we are meeting our requirements and that our requirements are correct. All the work that we spend in building and developing these models is not wasted because you reuse this model or components of this model for real-time testing. You can automatically generate code for the control algorithm and test that control out in real time against some prototype hardware that you have. Additionally, if you do not have all your hardware available at once, you can simulate aspects of your plant system as well by generating code for those components. This testing, of course, continues to check that the requirements are being met. You reuse the tests that you have already established for the model, and you can continue to rapidly iterate on your design. Automatic code generation is also applicable to then implement your final controller in either software for a microprocessor, hardware for a FPGA, or even a PLC environment. This highlights 4 aspects of model-based design that can be summarized as follows. It provides a CAE solution for multi-domain system-level development of embedded controllers. It is using mathematical models to describe the system-level behavior of your complex equipment to improve your design. You can automatically generate code for real-time testing and implementation of your design from these models. And finally, testing is done continuously to let you find errors and conflicting requirements early in the design where they are cheaper and easier to correct. So the overall value of model-based design is as follows. First, it allows you to explore unique features through rapid design iterations and conduct cost-effective design trade-off studies through simulation. Quality is improved by preventing errors from reaching the hardware stage and by just overall reducing the rework in your design. Cost is reduced by minimizing the number of expensive physical prototypes required and in general reducing overall testing costs by finding errors early in the project when their testing is less expensive. And finally, time to market is improved by being able to get designs right the first time and by accelerating the overall development process.